Okay, so I am about to be calculating or deriving some Rachford-Rice calculations, Rachford-Rice equations. And in order to do this, I first got to explain what this is used for. So Rachford-Rice is used for flash calculations, which is to determine, so you're given a feed rate. In this case, we have like benzene is equal to zero point 0.4 molar, and we have toluene is equal to zero point 0.6 molar for this feed that's going in. And then we have a feed of vapor going out and a feed of liquid going in. So the flash calculation is what we do at a given temperature and pressure, and we're just trying to determine mole fractions and whatever. So we want to determine like four things. We want to determine our vapor phase, like what the amount that's in the vapor phase, the amount that's in the liquid phase, the mole fractions of everything in the liquid phase, and the mole fractions of everything in the vapor phase. So we have all four of these things that I'm trying to find. And to start, this is equal to F. So we have our F is equal to liquid plus vapor. It's very, very simple. And then we can further determine what this is going to be by F is equal to Z, which is the Z component, which is the combination of what's in the liquid phase and then what's in the vapor phase of each component. And so if you know that, you're going to know the total amount that's going to the feed. And so like FZI in this case would be, I think, zero point 0.4. So we've been using Raoult's law a bunch, which is XI P I sat. So the mole fraction of liquid phase times its saturated vapor pressure is equal to the mole fraction of the liquid phase times the overall pressure, or in reality, it's the partial pressure of the component, but it's really going to be equal to the total pressure if you multiply these two together. So for that, we have a Ki is equal to Yi over Xi. Ki is just the ratio of what's in the vapor to what's in the mole phase for each component, and I'll show you how that's going to be useful. Our Rachford-Rice starts out like this. The sum of all things in the vapor phase minus the sum of all things in the liquid phase is equal to 0. And why this is because if you add up all the yi's, or like all the components in the liquid vapor phase, they all have to equal to 1. So you're essentially doing 1 minus 1, which is why it is 0, and why this works so well. But you could also just combine this to be y I, or all the sum of 1 minus xi, and of course I'm not going to remember to notate this the entire time, but for the sigma, or the summation, it's two n components, and you can have the minimum of one component, and then it's integer values from there. And yeah, you can see this a little low. I switched to red because this black marker here is dying. So our first substitution for this derivation is we're going to substitute. So if you'll notice in this ki, if you multiply xi, or xi by ki, is equal to yi, because you're just dividing, it's just multiplying both sides by x. So we can substitute this yi here for ki xi minus xi, and you'll notice again we can take out this xi, which it'll just be this, so it'll just be xi, I almost want to call this chi, but I know it's not, and then ki minus 1. And we'll leave that there for a second because we have some more derivation. And where that happens is we're going to determine that L is equal to F minus V. So we can substitute that for this equation, and then we just have, let me start a new area, F of the overall mole fraction is equal to F minus V times V times the liquid fraction, and then, yeah, I did this right, and then minus plus V times xi ki. So there we've got that. And then if we want to isolate this xi term here, so we do, because we could take it out again, so it's fzi is equal to xi f minus v plus v xi ki. That is there. Okay, so more manipulation, and we're going to find that, well, first I'm going to simplify this, and this is just going to be, switch the order of this around, and it's, oh wait, the xi isn't in here, so it's just ki, v, ki. Take a v out for these two, so it's v ki minus 1 plus f. So that's that, and then you just plug that in on the other side if we're isolating xi, so xi is equal to, well, I'm going to write this a little closer, xi is equal to, we're going to squeeze this in because I don't really, oh, looks like I can't not rewrite it. So anyway, if I'm going to have to rewrite it, it'll just be z f c I times ki minus 1 over, no, it's fzi, and then it's v times k minus 1. I did the wrong thing. Ki minus 1 plus f. And then we can take an f out of everything and just divide everything by f, so then it'll be xi, or let me just do it this way. 1 over v over f. No, it's not 1, it's zi. Then it's just vf ki minus 1 plus 1. And there you go, that is xi. And what we'll finally be able to do is plug that into the summation and get the sum of zi ki minus 1 over v over f ki minus 1 minus 1 plus 1 equals 0. And we're going to plug this into, eventually we're going to plug this into Python to be, ooh, almost dropped this. We're going to plug this into Python to become, and find this v value here, since we know everything. We know the zi, the ki, and once we know this, I've determined v, so I'm just going to write v here for this. And then once we've determined that, we plug this v in here, and then we get, I'll just do this one. We get xi with this, and then we can plug that vi xi into there, or no, well, we can plug this v also into here and get L, right, wrong side, L from here, and then use this equation to finally find yi. And I'm not going to obviously do this by hand, that will take way too long when a computer can do it much faster. So there we've just determined all 4 of these constants. Not constants. Well, in a moment, I guess they would be constants, but they're really not. They could easily be changing over time. So yeah, that's how you determine the Rachford-Rice calculation. Okay, so I'm going to explain something called the lever rule. So first off, you've got a PV. Let me draw this bigger. So first off, you've got a bubble dew pressure diagram, right? And you know, it's like something like this, and then another thing like this, and then they meet up somewhere over here. Okay, so that's all standard, right? And it's at some set temperature. And what the lever rule is you have, let's say, anywhere from 0 to 1 amount, and you just choose a random tick mark in the middle, right? Z1, and that's what you set that to. You have a Z1 component. And so that, and let's say you're at a certain pressure where it's like somewhere in between these two curves. So what that means is that you have, if you go immediately to your left and to your right, you'll have the y1, and then if you go, or well, your right, you'll have the y1, and then you'll have what's in the liquid phase on the left. So that is, and then these correspond to tick marks down here. So this will be like y1 and x1. Okay, so that's what those tick marks all mean. That's the basic diagram for this lever rule. And the first equation we're going to use is F equals L plus V, because we did that last time with Rachford-Rice. And then we've also got the F Z1 equals L x1 plus V y1. So the amount of liquid times, or the liquid is the liquid fraction, vapor times vapor fraction is equal to the total feed. And then what we want to do then is, so F equals L plus V, so we just replace that with L plus V. And we distribute, so we get LZ1 plus VZ1 is equal to LX1 plus VY1. And so then we put these each on their own side, so we go LZ1 minus LX1 is equal to V VY1 minus VZ1. And then we could take out the L's and V's, so it's LZ. Let's just do Z minus X equals Vy minus Z, because you know it's for compound 1, or really you could put I, so it's for any compound. I just put 1 because we have, let's say, 2 compounds, benzene toluene again, as has been a staple for this homework. And then we can simplify this to be V over L is equal to Z minus X over Y minus Z. And what that is, this is Y minus Z, and this is Z minus X. So that's where you get that, that's where that comes from. I could have skipped straight to there, but I kind of had to go through this whole derivation first. And so let's say you start out down here and you're all in the vapor phase, right? And then as you slowly increase pressure, you get, or well, realistically, you would just start here. So as you start the pressure right here, you are all in the vapor phase. As you start to increase your pressure, you get to this middle point where I showed the first example. So here, this is just purely Y1. You're all vapor. So as you continue to increase pressure, then you get somewhere in the middle, and your ratio of vapor to liquid starts to increase. No, decrease, because it starts out as 1 over, well, let's say almost 1 over next to nothing. Yeah, almost the entire Z over next to nothing. And then it'll get smaller and smaller and smaller until it eventually reaches essentially 0, because it'll be what, 0 over 1, which actually makes more sense than 1 over 0. You can't really do 1 over 0, but that's why I said just a little bit more. So then you start tracking more and more up, and then you have just X at that point. Let me differentiate this. You have just X1 there, right? So as you increase pressure more and more, you're going to get more that is in the vapor phase, or more that is in the liquid phase. And that's true for even just a pure substance, not just a mixture. So as you increase pressure, you're going to get closer and closer to the liquid. And this will track for any of the components as well. They'll all have slightly different PV diagrams because they all have slightly different saturated vapor pressures or yeah, saturated vapor pressures. So you're kind of gonna get a mix of everything in that. And so yeah, that is what the lever rule is, except it's not actual levers. It's just pressure and volume. No, it's just pressure and amounts of stuff. Okay, so now I'm going to be coding the Rachford-Rice equation. And I've got all my lovely, lovely equations. I had to erase like the entire Rachford-Rice thing because I did the lever rule in between this. So I have the knowns and then the equations that I'm going to need for this. And I did not finish writing out the xi, but I think it should be zi over 1 plus v over f ki minus 1. Yeah, sounds about right. Okay. Let me make sure I'm actually recording. I am. So, first we want to specify the temperature and pressure. That's kind of the main thing. So we've got this big T is equal to 393 kelvins. And then we have pressure is equal to 150,000 pascals. And then the next thing I need is going to be Z, and this is just going to be an array. So Z is equal to an array 0.4 and 0.6. Because that's, we have 0.4 is benzene to 0.6 toluene. Let me run that, make sure that's okie dokie. Oh. Okay, well I got that wrong anyway. Let's see how we do an array. Okay, never mind. It is... No, I did the array right. It just doesn't... Yeah, I need to run all. And F is equal to 10 because we have 10 moles per hour of all this. And this is just the for 1 molar. K, I... I'll just label this as also. And then as specified last time, we have Ki, which is going to be equal to P sat over pressure. And then we're ready to define our Rachford-Rice. There you got our old Rachford-Rice here. Some vector, well, I shouldn't have the space. I don't think it likes space. In terms of some vector, and we have our v over this. So let's just say v underscore f. I don't think I could do v over f. So we have our v over f is equal to this vector, but just the first value of the vector. We return how do I always end up managing to misspell this? And we want to return 1 plus v underscore. It is z over 1 plus v times f, or v over f, and then it's just k minus 1. Yeah, okay. So we return that. Oh wait, this needs to be a summation. I don't know why I didn't write that, but that needs to be a summation. So it's just numpy sum v f is equal to the root of our Rachford-Rice and 0.5, and then we just want that x term that this is going to produce, and then just the first term. So we have that, What are you talking about? What do you mean this doesn't exist? This is a valid name. V is equal to V V underscore F times F, because it's V over F times F. Let's try the brackets, because that's what I seem to have to do all the time. That does not work. Oh well, I've already screwed up because it's the wrong summation. I did the one for xi, so it's actually z times k minus 1. That's not going to make much of a difference because this error is not related to that. So I don't know why it says it's not callable. Did I? Of course I did. Then L is equal to F minus V. And from there we also have K, no, we've already defined K. X is equal to Z over, let's just copy paste this because I don't want to write this again. So that's what that equals. And then we have Y is equal to K times X. And that's just gonna be print, and regular Python, this is just printf, so it's print vapor, no, feed vapor is equal to, this is where I can use these, V underscore F. I feel like this number's wrong. Shouldn't be that, so I'll fix that in a sec, but I just want to get all these print statements done. Copy paste this. Mole vapor, the total moles of liquid equals L total mole vapor, and then it's just, so vapor mole fraction what is this? Okay, well, no, I just want equals, and then I want Y, and then I want liquid mole fractions. Yeah, these numbers are not quite right. I guess I'll just try to, I think it might be, I think I have an idea of what it is. It should be p dot pvap. Should just be p dot pvap t. I didn't like it, me doing it up there, so we try it now. Nope, still not it. So psat, you can stay. Wait. Oh no, they did change. The numbers did change. Okay, so it is p dot pvap. I have no idea why it works like that when I'm pretty sure my psat up there was the exact same thing. Yeah, B side equals P dot P dot T. Oh, okay, well, if it's being picky, I'd probably use this value. If I had to guess. Okay, so that is how you code the Rachford-Rice equation, or you can call it the Rachford-Rice method as well.